Yes, that's it. It's good. We can start.
Okay, we have Patrick with us. Well, then we have everyone and a few more. Excellent. It's sharp on the hour. Thank you very much, everyone, for joining us in joining our session. Our session is just to be sure that everyone is in the right room. This is on electric vehicle scenarios. And if you were going to present somewhere else, then you're in the wrong room. But without further any delays, I think it's let us welcome Ana Carolina Cordeiro with as our first presenter. Well, the rules are as you have seen before: 20 minutes presentation, about 5 minutes for the questions, and we are not that many in the room, at least at the moment. Please, everyone, get involved, get engaged in each other's papers, and ask questions and so on, so that we get the most out of this session. So Ana Carolina will talk to us about the economic attractiveness of electric vehicles in Brazil, importance of incentive policies. We have a diverse, we will have experience and cases from different parts of the world, which is one interesting sort of feature of this session. So Ana Carolina, the floor is yours, please.
I need to be able to share my presentation. I don't think I'm able now.
Now you cannot share your screen?
Don't be surprised
no.
if I interrupt you.
I can share my screen now.
At the end of your presentation.
Okay, and now?
Now I can. Thank you.
Perfect.
So we stick to the schedule.
Are you seeing my screen? Okay, I will. So now I will present my paper. It's about the economic attractiveness of electric vehicles in Brazil and the importance of incentive policies. I'm from Brazil, Federal Fluminense University, and it's my paper with my advisor, Luciano Losekann. So I will start presenting an overview about the case. The concern about the climate effects of greenhouse gas emissions has motivated the search for less polluting alternatives in the transport sector in general. So EVs diffusion is one of the ways to reduce the greenhouse gas emissions. So I will start talking in general, not about Brazil. So EVs diffusion, the concern about the climate, of course, it's a point to promote EVs. And in addition, EVs diffusion could help to achieve other objectives, like the reduction of oil dependence in important countries, the reduction of noise in urban areas, and improve the air quality. As challenge, we can highlight the high cost of batteries and the lack of charging infrastructure that implies in range anxiety. That is the concern of finding charging stations. So I'll start presenting a case of the Brazilian fuel. We had an experience with ProAlcohol, that is a program, Brazilian program, the national ethanol program in Brazil. After the oil crisis, Brazil adopted in 1975 the national ethanol program called ProAlcohol. As we can see, we have a increase of sales of ethanol vehicles, and the government was the Brazilian government was very interventionist and make measure protections, so protection measures. So they have succeed. And although in 1986 the price of the barrel of oil in the international market reduced, which hampered the program of substitution of fossil energy. And in 1990, since the cheap oil made it unfeasible to keep subsidies on ethanol, the ProAlcohol program was discontinued. I think it's a case that Brazilian had already had an experience with a widespread of the diffusion of an alternative technology on fuel. So I start presenting this case. And we have flex fuel vehicles. It's more than 80% of vehicles in Brazil are flex fuel vehicles. So it's an important case. And the Brazilian market has the characteristic of adding ethanol to gasoline, which generates the need of mechanical adjustments of the engines. So Brazil had to adapt car engines. In addition, the country already had an ethanol distribution and marketing infrastructure that helped the diffusion of flex fuel vehicles. In March of 2003, Volkswagen started selling Gol, the first flex fuel vehicle car in Brazil. But it's important to note that this experience with ethanol and flex fuel vehicles are different of electric vehicles because ethanol and flex fuel cars use the same supply infrastructure, which is not the case of looking electric vehicles that need the charging infrastructure. But it's important to see this case of succeed of alternative technologies. It's the characteristic of Brazil. And as you can see, in 2018, electric vehicles they didn't start the diffusion yet. So the Brazilian case. The Brazilian electric vehicle is mostly renewable. That's a characteristic that can be an advantage in the diffusion, since it allows the electrification of transport to imply lower emissions. As you can see, we have hydro, and also is increasing the participation of solar and biomass. However, Brazilian has a concentration of the fleet low acquisition value cars. And moreover, the lack of charging infrastructure is a challenge in a country with continental dimensions. But as you can see, we have a domestic electric supply that is very renewable. So I will present a feasibility study. So I compared 3 types of cars, Toyota Corolla, Toyota Prius, and Nissan Leaf. The purchase price in reais, and we have the difference between a high difference of purchase price. And we assume that a consumer lives in Rio de Janeiro and drives 1,500 kilometers per year in the city and resells the vehicle after 4 years. So from Metro data, we collected the energy consumption data of Toyota Corolla and Toyota Prius. And from US Department of Energy and US Environmental Protection Agency data on energy consumption, we consider an approximation of the mileage values per liter for the Nissan Leaf that a gallon of gasoline is equivalent to 33.7 kilowatts hour. So here is the purchase price, the fuel supply, the city, kilometers per liter, and the resale price after 4 years in reais. So as you can see, you have a big difference, but the fuel supply can help the diffusion. So here I compared the 2 types of cars. Hybrid vehicle with a normal vehicle, usual vehicle, Toyota Corolla, that use fuel, and a Nissan Leaf and a Toyota Corolla. So here it's the moment of the purchase, and I put here in the cash flow the difference between the prices of purchase of Toyota Prius and Toyota Corolla. So I put it as a negative value here in the moment of the purchase. And after I measure the fuel economy per year in reais that we can gain. So here is the first year, the second year, the third year, and finally the 4th year with the, here you can see also, also I included the resale price here in the cash flow. So here, a negative value in the moment of the purchase, the fuel economy per year, and after the fuel economy with the difference of the resale price. Here you can see the difference of resale price, and I added here with the fuel economy. So as you can see, the net present value is a negative value. So even with the fuel economy, it's not economically attractive to purchase a EV in Brazil nowadays. And after I compared the battery electric vehicle with a Toyota Corolla. And in the moment of the purchase, you can see the difference between the values of the purchase price and after the fuel economy. The fuel economy is bigger than the first case, but the difference between the purchase price are very, very high. So as you can see, the net present value is negative. It's also negative, and it's a big difference of the first case. Even with the higher fuel economy, we have problems with the acquisition value. So the results, the fuel economy afforded by the hybrid electric vehicle Toyota Prius is not enough to make the vehicle economically attractive due to the high vehicle price. The same goes for the Nissan Leaf. The battery electric vehicle reduces consumer spending because charging with electricity is cheaper than spending on gasoline, and battery electric vehicles are more efficient. However, the high purchase price makes the vehicle even less attractive than Toyota Prius. It will be necessary to drive about 37,000 kilometers per year so that the consumer will be neutral between these two vehicles, Toyota Corolla and Toyota Prius, under the conditions considered in this study. In the case of the Nissan Leaf, it will require an even bigger run, a total of 75,000 kilometers per year. We can read the net present value presented in this case as the amount of subsidy that needs to make these vehicles attractive. Here, the amount. Therefore, policy in different areas will be necessary to make these vehicles attractive. As incentive policies, we can highlight purchase, subsidies, tax and sanctions, free parking, permission to use expressways, and the construction of charging infrastructure, reducing the problem of range anxiety. Here, to see, I made a simple profiles of potential adopter. Consumers with high incomes and who need to travel long distance have this type of consumers can have a high motivation for EV adoption. Here I put the mileage and here the purchase power. So we can consider 4 simple types of profiles of potential adopters, EV adopters. And here is the consumer with less purchase power, and here with high purchase power. And here the consumer that don't use the car a lot, they don't have to drive long distance. And here the consumer that needs to drive long distance so they can have the fuel economy. So here I can, as you can see, it's a very, very simple framework, but it's interesting to understand in each case, the case that needs some policies. All these cases need policies in Brazil because it's very hard, the division of electric vehicles in Brazil. But in this case, we need a high amount of subsidies. And here, not a high amount, but we need the subsidies. In this case, we can, as you can see, all the policies are interesting, like purchase subsidies, tax exemptions, and also non-monetary policies, like the permissions to use expressways. But in this case, we can consider like taxis and Ubers, and it's important to note that they need more monetary and non-monetary policies, but like they have a very big range anxiety. They need to charging stations. So this type of consumers are very important to focus on the charging investment. And here, this type of consumers had high motivation for EV adoption, but it's interesting for them non-monetary policies. And for these ones, low mileage drivers, it's interesting to they have high purchase power, but they don't procure mileage a lot, so they don't have the fuel economy. But the important thing is that all these profiles had the need of incentive policy, but some of them need more. And some of them are interested in charging stations, like the ones that with high mileage, and some of them prefer monetary policies, like the ones that don't have purchase power. So the conclusion, as the biofuels sector is well developed in vehicles with low acquisition values are the majority of sales in Brazil, EV adoption tends to be slow in the country. The feasibility analysis shows that the large amounts of subsidy are needed to allow the EV diffusion. It is important to note that even though the consumer has no budget restrictions to purchase a vehicle and use the vehicle for long distance travel, policymakers need to adopt incentive policies for these potential consumers to become EV buyers. This is because under the current purchase conditions in Brazil, EV is not attractive. However, the Brazilian market may experience particular solutions, such as hybrid and electric vehicles that have recalibrated auxiliary combustion engines for the use of ethanol. EVs may have niche markets in the certain areas that have greater incentives to adopt them, such as urban centers with poor air quality, and thus we expect a late diffusion of electric vehicles and the coincidence of different automotive technology in the coming years. Thank you very much.
Thank you very much. Very good, and for keeping the time and even saving us 2-3 minutes or so. Thanks a lot. I do have one question from the audience, but I will take the opportunity and go ahead with the first question. Perhaps that was sort of from the beginning I was wondering about, and also even more towards the end. When you talked about those 4 boxes, that they were interesting in terms of affordability and mileage and so on. But there is something between conventional cars and electric cars, which is, you know, in a certain way, which is called public transport. I mean, some of those public policies and subsidies and so on, don't you think that you will start, so you might actually push some of the people towards electric cars who are actually on public transport already, by making it more sort of more easy and far. I mean, it's not only negative, I suppose, but have you tried to consider some of those unforeseen consequences of that this might of that kind that this may have?
Can I answer now?
Yes, please.
Okay. I think if you use incentive policies for the purchase of vehicles, we have this kind of problem because we are not incentive the transport, the public transport. So in this case, I studied the purchase of cars. So it's hard to talk about the transport, the public transport. But I think it's important to incentive, first of all, the electrification of the transport, the public transport.
Yes, because in transport, what's important all the time is that people have a choice, and they're given, if you take something from them, you give them an alternative rather than maybe just taxing them or penalizing them for the way they are doing something.
Sure.
I have a second short question as well, because I see we have a little bit of time. But the financial incentives also, we have seen it, for example, sort of the case of Norway comes to mind. If people become wise enough and realize that these subsidies are not going to last forever, and the support policies and so on, they will be taken away one day. This is part of an innovation policy, right? What if people start taking that into account and incorporate that into their decision making and say, you know, this is just for a period, and even things will have to go back to normal one day, and these subsidies, they will be clawed back.
I think the concern of climate aspects in Brazil are not very high enough to make the consumers decide to buy a EV now. And the monetary aspects are very, very important because we have a fleet concentration in low acquisition value cars. So it's hard now to the concern about climate aspects to change the mind of the Brazilian consumer now.
Well,
it's a process.
Yes.
It's a process. It's very hard now.
Please allow me to read this question from I'm not sure from who it is in the audience, but this is the analysis doesn't consider the maintenance costs of vehicles. Do you plan to expand the analysis to consider that? It may affect the results given that EVs have much lower maintenance costs. Also, a lifetime of 4 years may also affect results. Do you plan to run a sensitivity analysis with different vehicle lifetimes?
Of course, the maintenance costs are very important. They are low in the case of EV, but it's a simple model. Of course, now this paper is about my master thesis, and now I'm doing the PhD, so I can explore more these aspects that I didn't search in the beginning. But of course, it's very important.
Yes, excellent. Then you have a question from Patrick, right?
Yes, thank you, Tooraj, for letting me speak up. And also thank you, Anna Carolina, for this interesting presentation. I appreciate it also because I'm also interested in the electrification of Brazilian vehicles. My question refers mainly to the charging infrastructure, because to my knowledge, it's quite hard in Brazil to establish charging infrastructure because of the grid problems, and also at least the inner cities are usually very dense. In Germany, we have the advantage that we have quite spread out cities and also very tiny cities. So most people can charge at home, which is very costly and very, very fine from the cost perspective. So my question is, how optimistic are you about the home charging possibilities, or do you expect that everybody may charge even at the public space, which is much more expensive?
I think that nowadays the solution is home charging, or maybe in the work. We have some spaces in centers of work, and also maybe in malls. And because now, as you said, we have this kind of problem that is not common to have charging infrastructure in homes. But maybe in the space of work, I don't know exactly how it could be, but it's a way, I think so. But I think the home charging will be the main charge.
Okay. In your current cost calculation, how did you consider the charging cost? Is it just the electricity price, what you considered, or did you also somehow consider the infrastructure?
As we don't have lots of charging infrastructure in Brazil, I consider the electricity price in homes.
Okay.
Yes, because we don't have enough charging points, so charging stations. So I consider the electricity in homes, the electricity price in homes. Thank you for the question.
Thank you too.
Okay, well, Patrick, so while we have you there, shall we move to our next paper? Thank you very much again, Anna Carolina.
Thank you very much.
Many thanks. Our next paper, how to aggregate load shifting potential of electric vehicles for energy modeling, for energy models, by Patrick Jochem from German Aerospace Center. I have a little of familiarity with your center. So please, Patrick.
Yes, thank you. I hope you can see my screen already.
Can you share your screen?
Yes, I can.
Okay.
It's coming.
Is it visible now?
Yes.
Yes.
Great. Okay, I see, you can see it. Okay, so this is work which I've done in Karlsruhe, where I was working for 10 years, working on electric vehicles and how to integrate them into the energy system. And this is work which I've done together with Sabrina Ried, who cannot be here, unfortunately, today. And then Thomas Dengiz and Sebastian Soldner. And what we was thinking about is how to integrate these load shift potentials from electric vehicles into energy system models. Because you and we will see in a few seconds that this is a quite mathematical challenge. And I'm optimistic that some of you can help me and us with this problem. So I would like to motivate and introduce the topic first, and then I will sketch 4 potential mathematical ways to integrate electric vehicles into energy system models. So in considering the load shift potentials for shifting electricity from one hour to another. So the first method is single charging events. The second thing is that we consider a single EV over a time horizon, like a week or a year, where we can then consider the load shift potential for a single vehicle. And then we go to an approximation or a very simple approximation of EV fleets. And then we come to a more mathematical interesting part where we aggregate the prototypes. And then I will sum up. Okay, I think we all know in terms of renewables, especially, which are depending on sun mainly and wind, we are facing challenges in the electricity system. And so we need more flexibilities in other technological appliances. And one promising and very promising approach is to consider electric vehicles as mobile flexibilities, because they have this very long standing times. In Germany, a current vehicle is used for only less than 1 hour in average per day. That means that it is parked 23 hours a day. And you know that storage in electric vehicles is quite substantial. Usually we have 35 kilowatt hours or even more today. So the load shift potential is amazing, especially if we compare it to other technologies. It's even cheap. Yeah? And even if we look at, if you look on the energy content we have in the electric vehicle, this is amazing. For an usual private household, for example, the energy demand from an electric vehicle is more or less the same than for the rest of the household. It's a bit less than that, but it's comparable. Okay, but now what is influencing the load shift potential of electric vehicles? And here I have 2 examples with me on the right-hand side. So the first thing is, of course, the charging rate is influencing the load shift potential. So the higher the rectangles are, for example, you see here, it's a quite high rectangle, so the charging rate is quite high. And the longer the rectangle gets, the longer the parking time gets. Yeah. So what we have here is the typical fast charging process. So short time horizon, high charging rate. And for example, this is a typical night charging process, usually about 14 hours or so. And what we have done additionally is that we indicated in green or red color whether we have a flexibility or a charging need. So the red color indicates that we need electricity for doing the next trip. Yeah? We assume that we know the next trip, for example, let's say 50 kilometers, and we need that amount of electricity. So in the lower case, you see that we always have this red part within the box. So we always need a kind of electricity demand during the charging process. But in the first 2 boxes, the flexibility is still very high, even though we need electricity. While on the 3rd box, we see in this fast charging event, there's no flexibility. So we need the whole parking time for the charging. Yes, and the green area is the depth of discharge, which is the battery capacity minus the SOC, so the state of charge. So this is the flexibility I have in the battery. So if I would arrive with a full charged battery, which is very unlikely, in that case, the green box would be very close to zero. Yeah. So usually the cars arrive, of course, with a kind of rest capacity for charging. Okay. So in that case, the flexibility is quite high. In that case, it's a bit lower. But you see, even if we look only on this sketch of charging processes, it seems to be difficult to identify the load shift potential of electric vehicles. Because it depends on the time frame, on the time of the charging process, and also on the charging rate of the SOC value, so the state of the charge of the battery, and so on. Okay, so this is really something which is even complex for a single car. And you can imagine if we now consider different cars, it's getting more and more complex, because many also, they are not parking at the same time. So as you can see on these two example cars, this vehicle, the lower vehicle, is departing a bit earlier than the upper one. And so to sum up these flexibilities, it's getting complex. Yeah, and this is what I would like to talk about in the next couple of minutes. So the research question we are focusing on is how to consider these flexibilities of thousands of electric vehicles, like in a country or even more than that, in energy system models. And the next question is, and is the main question, which methodologies are used for aggregating electric vehicles' load shift potentials? Okay, so the first class of literature we found is the most easiest one, of course, is that we just consider one single electric vehicle and we look what kind of flexibilities this electric vehicles has. And of course, I can show you very easy pictures for that, but I decided not to do that. I showed a bit more complex illustration. In that case, what we have done is that we consider different prices for charging, and we see a dedicated charging process, which started at Tx arrival until Tx departure. And in that case, we assume that the vehicle users indicated a minimum range. Okay, this is something which is proposed by many researchers, that we should never use the whole flexibility of the battery, but we should assure that, for example, every user can go to the next hospital. So let's say 30 kilometers rest range or minimum range should be included in the battery at any time. So in that dedicated charging process, the SOC arrival was below the minimum range. That means that the charging schedule is usually starting immediately after plugging in until the minimum range is achieved. And after that, we have a flexibility, which is then illustrated in the next rectangle. No, it's not a rectangle. I don't know what that is. So you see here, it's still charging because, for example, the price was low, but then we assume at least 2 stops of charging in between. Yeah. Okay, so there's no vehicle to grid yet, but you see, even though when we look to a single vehicle, it might be difficult to measure and illustrate the charging flexibility of this single car. Okay, what we need for that is the charging data, of course, also the SOC before and after the charging event, then maybe also the efficiencies for the battery and electronics in order to consider also efficiency losses, and probably also the charging power curves. That means when you look into the charging behavior for a whole charging cycle for the battery, and you have here the SOC value, so the state of charge of the battery, and you have here the charging power. Usually what you can see in low SOC levels, the charging power is quite constant, but in order not to harm the battery, after a while, the charging power drops down. And this might be also considered by this energy system models. Okay, even though it's already quite complicated, it might be easy. It depends on what kind of technology considerations you consider. So even there you can get some non-linearities, which is of course painful for the model because it makes it much more complex compared to linear approximations. And then, of course, you cannot implement this complex single consideration of cars into big models. So what usually people do is that they just look on a single electric vehicle, but they consider the single electric vehicle over time. And they assume that this single vehicle is used for a certain time horizon. And what they do is that they have a maximum SOC level and minimum SOC level. So what means is that in the lower one, which is an extreme case, the modelers assume that the electric vehicle user is only charging the electric vehicle for the next trip and always as late as possible. So the battery is as empty as possible for the whole consideration. And the other extreme is probably closer to reality. Here we charge always as soon as possible and as with highest charging rate as possible. And what the authors argue is that here in between we have this flexibility. So we can choose each point between the two lines, and this is an application which is possible. But of course, this is an extreme scenario and probably not so much too close to the reality. And also the question is whether there's a connection at each charging point available to the grid. And usually the people don't consider this. Okay, of course, advantage is mathematical wise, this is easy. But of course, it's a very huge simplification, not only from a technical perspective, but also from a user acceptive perspective, because we don't think that people will behave like that, even though they might be compensated from a kind of tariff. Okay, let's come to the third approximation, which is then now considering already fleets. So what they do here is really to consider many different electric vehicles which are arriving at certain times and departing at certain times. And they really implement these fleets like electric vehicles, and they can consider a kind of 100 different electric vehicles, at least if they assume that the charging is linearized, so simplified. And if you consider electric vehicles like that, you can think of that you have just kind of bricks like here, and you can just take 100 of bricks, which is one charging behavior, and you can just allocate them wherever you would like, at least as long as the time horizon is still within the parking time of the single vehicles. Okay, and again, we need this minimum and maximum state of charge for the vehicles. Of course, also the total discharging energy due to driving for the next trip. And of course, also available charging power. Usually there is an assumption that all vehicles charge at the same charging power, let's say 10 kilowatts. The advantage is clear. The complexity is low. But of course, we may have mistakes in the results because we usually overestimate the flexibility. This is what I show in a few seconds. Okay. And of course, also in the method above, so in this method above, also the load flexibility is usually overestimated. Okay, let's come to the last option, and this is the most complex options. So what we do here is, or what we did here is that we now really consider every single electric vehicles, and we constructed a matrix, yes, where we consider the charging power, minimum and maximum, and also the different boundaries for the SOC values. And then we can take these values in this mathematical representation. And then we can consider several hundreds of electric vehicles. Yeah, but even though it looks simple in that way, because in that case, the two electric vehicles are parking at the same time slot. So here you can still recalculate that this summation becomes this, at least in the 2 dimensions. But if we now have another dimension like the charging power or different arrival times, then you can imagine that the problem becomes much more problematic and more challenging for the solver. Okay, this was not surprising. We found 2 dissertations which analyzed this problem, and we did also our own consideration. And for a few time slots, this was very easy. And you can imagine, especially the time slots are showing the problem, because then we have, if we consider 10 different electric vehicles, and if they arrive and depart at different times, this problem becomes very big. And you see, at least in that case, the runtime exploded after 9 time slots. So it was very hard to calculate more than 10 time slots.
Patrick, 3 minutes.
3 minutes, perfect. Yeah, I will do that. So what comes out is, even though it is mathematically possible to do this Minkowski sum, yeah, but for higher numbers of time slots, which is the usual case in energy systems, usually we have more than a few thousand time slots, we need definitely a very good approximation. And this is where we currently stop our research, because we don't get any good approximation of that. But we have already 2 first attempts, which are providing small steps, still not possible for do national considerations. But I think it's worth to go deeper into this research direction. And because I promised a few seconds ago that I will show you that also the results differ in energy system models depending on the different methods. Here what we did is we considered different methods how to consider the electric vehicles in energy system models, and you see that the results are quite different. So this is the a consideration, for example, of gas, wind, and PV power plants in a very small energy system analysis, and we see the results are different because the load shift potentials are also different from electric vehicles. So it is important to consider electric vehicles in a precise mathematical way. Yes, and this is also to sum up what we did. So mathematically exact is, of course, a good approach from a scientific point of view, but we cannot do that in national energy system models, and also not in more than 10 time steps if we use the Minkowski sum. And so we are very much interested in cooperations in this regard, that we have an approximation method which can easily consider several electric vehicles in big energy system models. And we published our idea already in this paper. And with this, I will end and hope I will get some insights from you in order to start new cooperations or to solve this interesting problem. Thank you for your attention.
Thank you very much, Patrick. That's excellent, and that's exactly what we are here for, to do some networking as well on the side. This is great. I would like to invite questions from the floor. I don't see one right now at the moment, but we can give people a minute or 2 or so for these to emerge. Can I then let me ask my question then, while we're waiting for others to organize their thoughts. Patrick, this was very educational. I liked what you did with the slides and so on. It was like being in a classroom, which was and as you said, it's a very complex type of question, and you made it seem a little bit easier than it actually is. I'm sure it's a lot more complicated. You were being modest. So, however, I can imagine 2 more complicated things than that. That sort of your model kind of faces in the next stage. And one is, I mean, you have identified a possibility that, for load shifting and so on, that others have also identified it early on when they thought of aggregating electric vehicles and so on. So there is a value to be had out there. So here I'm thinking about business models as a vehicle of making this a reality. So, as with many other energy technologies, what does it take for this to actually start becoming a kind of sort of reality as a part of as a business model? And why and we probably know about some of the difficulties of it and so on, and there are very serious issues to overcome before you can have a viable value proposition, so that becomes a vehicle of carrying these sort of out, and in the process also deal with something even more complex, which is the behavior of the individual consumers. We are very well familiar with it from the retail electricity and energy market, how people behave, in some weeks, the low price elasticity, and it takes a bit more than just money for us to change our behaviors and our movements. Case and so on. So do you have any thoughts about how we go from here, so that this can be part of implementation and solution, what you have sort of presented to us?
Yeah, brilliant question. Brilliant question. Thank you for that. I think this is really a very interdisciplinary research topic, because what I have learned is that if we have a market share of more than 10%, many grids, even in Germany, and I know that German grids are quite good, even German grids may run into problems. So I'm very optimistic that we will have a kind of incentive, technically or economically, to influence the charging behavior of customers. So there I'm very optimistic that there will be some attempts. Yeah, but I'm with you. I don't know how this may work best, because I agree with you that the users are so heterogeneous, and this is a big challenge to convince the customer to allow us to influence their charging behavior. And this is also a very broad research field. It's not mine, but I'm looking from time to time in this research field. I think this is something we should do together with other research areas to consider the electrotechnical impact on the grid, to look on the psychological behavior of the customers, to consider also the economists, to say what kind of instrument might be the best one, and so on. And so we need an interdisciplinary approach that failed. Yeah, and I'm with you. I'm only doing a puzzle of that, which is the mathematical modeling. I think it might be an easier one than having a good recommendation for how and which policy instrument should be implemented.
Yes, well, I'm an economist. I always say, who is going to do this and how much?
Yeah.
I have a hands up from Yannick Press. Yannick, please.
Hello, Patrick and Tooraj. Thank you for the presentation and for allowing me to raise a question. I don't know if it solved the problem, but one PhD of mine is trying to solve this type of problem, but not on the, let's say, not on the national scale, but more on the distribution side scale. And he's using an agent-based modeling to see how the cars could learn how to recharge in a smart way, giving their next trip, how many the state of charge of the batteries, and what we are supposed to do in the coming days. And I think it's probably a way to do the aggregation, but in let's say in the middle of the two extremes that you are presenting, which is approximation and mathematically exact, which is to allow a learning process of the cars to see what they can do and what they can't by a process of making each of them learning what to do.
Yes. Yes, Yannick, thank you for that. And I'm interested in this PhD students because I know that you have only very good PhD students. That's good. And what we did in the first case also something similar. And this, at least this illustration here is also coming from an agent-based model. But in the agent-based model, at least to my understanding, you have still the problem that you cannot identify really the load shift potential ex ante. But you see only the results at the final stage because it's a simulation model, isn't it?
Yes, but I think you could try to have a sort of history of the decision taken, and then you could make this the calculation of the sphere or the integral that you need. You can rebuild it through the step what the car is doing.
That's a good idea. Yeah. So do some learning.
Yeah, and then by the trajectory the car is taking, you could approximate this range of action, in fact. And it's the PhD of Felipe González Venegas. Is supposed to be defended in July, so I could send it to you if you are interested by what is inside. But you are right. It's a huge problem to find the good and the fine tuning between precision and say something smart. The more precise you are, the more it is complicated for the system point of view to say something.
Yeah. And do we know whether the PhD students also compared his simulation results with an optimization approach? Because usually simulation is close sometimes to optimization, but we sometimes don't know how close we can get. And it might be interesting to compare this simulation and learning approach with an somehow done optimization approach.
Yeah, the problem is, as we are trying to understand in UK, in Netherlands, in France, the new tenders for flexibility provision, we try to understand how much flexibility each car could provide with a certain threshold of security. So it's not yet an optimization model. It's more like how do we learn what we can do and what is the range of confidence we can have on the provision we could deliver without paying the penalty. Because in each of these systems, if you don't deliver what you have said that you will, you suffer the penalty from the TSO or the TSO.
Yes.
And of course, you need optimization is one maximum point that you could dream to get. But in fact, in practice, as you have many problems, you try to know what is the size of the cake you could try to attract.
Yeah.
But I think it worth the cost, Patrick, that I put you in contact with Felipe and you discuss the two of us to see what you can do together.
Oh yes, that's very interesting. Yeah, yeah. And are electric vehicles already common in these flexibility markets in France?
Yep. And,
yeah. Okay.
There is couples of examples in France, Netherlands, and UK.
Thank you.
Thank you very much, everyone. I think it's time to move on to our paper number 3. The paper is, I see a question by our next speaker, Remi Lauvergne. It's great that our speakers are engaging with each other's papers as well. So you can think about a response to him as well while he's speaking on, let me bring up the title again, on integration of electric vehicles into transmission grid, case study of economic impact of generation load adequacy in Europe in 2014. The floor is yours, Remi.
Yep. Do you see my slides, my presentation?
Yes.
Yes. Okay. So hello everybody. So I am Remi Lauvergne, and I will talk about my work on the integration of electric vehicles into transmission grids. So I'm a PhD student working with RTE, so which is a French transmission system operator and central Supélec. And this work has been carried out with Yannick Perez and Alberto Terreda. The outline of our presentation will be first to introduce the subject, and then provide an insight on electric mobility modeling, the demand modeling, before studying a case study on the EV demand, the prospective EV demand in France. So to begin with, as you know, in order to introduce my presentation, transport is one of the main CO2 emission sector in Europe, and we see that governments are promoting EVs and trying to plan the ban of thermal vehicles, for instance, in 2025 in Norway, in 2030 in Germany, Netherlands, and the UK, and 10 years later in France. And as a result, we have to expect a large EV development in Europe, but also elsewhere in the world. And as a result, researchers have to anticipate such a fast EV development. So we can imagine several sectors in which electric mobility interacts with the power systems, which are summed up on this slide. So first, on the year-long side of this graph, we see that there are issues which are subjects on the hourly power system adequacy and optimal dispatch of a generation mix, and also on grid flows at the local scale. And there is also two subjects which are closer to real time, which are short-term markets, so a day ahead or intraday, so less than 24 hours before real time, but also grid frequency, which is a matter of minutes and seconds. So in order to list the studies that are being carried out between electric vehicles and this sector, we can see that, for instance, on the first part, which is hourly power system adequacy, we have studies on the smart charging flexibility for generational adequacy, but also the CO2 emissions of transport sector. Secondly, for grid flows, we have both the impact of EV charge on the grid flows, but also how to optimize the sizing and location of charging points. When we look at short-term markets, we have how to value V2G fleet on those markets and how will aggregators behave on short-term markets. And lastly, when we look at grid frequency, we can look at both the impacts of EV demand and the system frequency, especially with smart charging, but also how can EV participate in a frequency regulation markets. So in the literature, what I found is that for the first part, we see most studies from consumer or aggregator perspective, but not really at the TSO and national level. And for the grid flows, most of the studies I found are at the local scale, so on the distribution system, but not a lot on the national or regional scale, which is the scale of a TSO. And lastly, for the short-term markets and grid frequency, there are a few studies in the short term, so what happens currently and in the 5 following years, but not much in the long term. So what happens behind in 10 years and 20 years. So the research question I'll be tackling today is focusing on hourly power system adequacy and trying to address the impacts of a large diffusion of electric vehicles at the national scale. And the following work will try to estimate how EVs can have an impact on prices. So in order to sum up my research question, I would say that to what extent and under which conditions can the electricity system accommodate a large number of electric vehicles in the middle to long term? So in order to answer this question, first I will talk about electric mobility demand modeling. So what I call demand modeling is summed up in this slide. So we see that on the left, we have data on trips of vehicles, and also we have to take hypotheses on the vehicle we model. And in order to get load curves of those electric vehicles, we use a vehicle connection algorithm, which I'll be detailing in the following sections. And after the load curve, a charging module can help providing EV demand curve according to several charging pattern, smart charging approaches. And I think this subject is what Patrick has tackled just before. So I think those representations are quite complementary. So when we look at mobility algorithms, we can sum up them into three main groups. So on the left, we have statistical usage of travel data, which rely on generating randomly travel data for each vehicle based on histograms or distributions from travel surveys. So I will detail this approach later. We also have two other approaches, which are in the middle approaches based on drawing a probability to switch from a state to another. So it's still based on a travel survey, but processed a bit differently. And lastly, the activity-based models, which rely on a more detailed description of activities and transport infrastructure that is being used. So I think these models are more precise at the local scale, but it's not easy to use them at the national scale. So as a result, I've selected the statistical usage of travel data for my study. So when we first look at the travel survey data that is being used for those models, I focused on the French National Travel Survey, which have been published 11 years ago, which is the last to date available. And we see that the travel data differ according to several parameters. So first, we can distinguish between what we call local mobility, so mobility close to home, which is basically commuting to get to work or to go shopping or elsewhere, and long distance trips, which differ a lot as vehicles often take the highways and drive longer distances. We can also separate travel data per residence area. And as we can see on this graph, drivers from rural areas travel much longer distances than in the biggest cities. We can see the distribution of the distances driven per residence area. There is also huge differences between the socio-operational type of EV users, which is something that's included into the French travel survey. And we can see that employees are much more predictable than other socio-operational classes types in which their trips are often beginning in the morning between 7 and 9, and they get back at home late in the evening, whereas students or unemployed and retired people have a much unpredictable trip rotation. And lastly, there's also differences between working days and weekends on the distances traveled, which I'll detail in the results sections. I will also identify something interesting that has to be kept in mind when we model mobility, is that from the data we used, there is a significant correlation between the distances driven every day and the trip times. And as we can see in these graphs, the earlier a driver leaves home, and the longer distance is driving on average. And it's the same with arrival time. The later a car arrives at home, and the longest he has driven during the day. So as a result, when we draw distances and departure times for the trips in our model, we try to draw them together, the times and the distances. So once we generate the fleet parameters and fleet planning for every vehicle, we compute their consumption. So we see that the main factors of EV consumption are the speed, the temperature, and the use of ancillary equipment. But in our model, we only modeled the consumption in function of the temperature and the speed of the vehicles. And lastly, after we select a time step, which is adapted to the study we are doing. So for my case, it's a 1 hour time step. We can generate the evolution of EV consumption and location per time step in the simulation. And lastly, it's also complementary to the discussions of last presentation. We see that there are, in the literature, there are some different recharge behavior, as you can see on the left, which are some EV drivers connect whenever possible. So every time they get to a charging station, they connect their vehicles. But as EV battery capacities are becoming larger and larger, we see that some drivers are connected only once a few days. So we separate them into two categories. The ones we connect only when needed, so which means when their state of charge drops below a given threshold, and other that connects only when convenient, because there are two main categories in those behavioral studies. And the when convenient users connect mostly on weekends. And of course, if the vehicle has planned to drive longer distances, he still connects even if it is a non-systematic behavior. So when we try to gather some results of EV demand at the 2040 time horizon, so first I try to study the most optimistic EV development scenario that I found in the literature. So in line with RT studies, we see that on this graph, the most optimistic EV development leads to around 2/3 of the fleets to be converted to battery electric vehicles in blue or hybrid vehicles, plug-in hybrid in green. So that's around 2/3 of the fleet in 2040. Reaching mainly 100% in 2050. And yeah, so our hypothesis of my case study are that yeah, if the repartition of BEVs and plug-in electric vehicles is around 85% to 15%. And the order of battery capacities, we took 78 kilowatt hours, which is huge batteries, but it follows the tendencies we can observe today. And you observe and for the charging points we modeled, we can see on the right that at home most chargers are 3 or 7 kilowatts, but on other areas we have some higher powers, especially on highway with mostly 130 kilowatts. So when we look at the results of the previous modeling approach I presented in section 2, we can see that on this graph I plotted the results for the 3 day types I modeled, which are working days, Saturdays and Sundays. And we can see that our hypothesis consider that most of the recharge will be done at or close to home, which are the blue and red recharge. But if we also model recharge done out of home in green or purple, we have also some demand all through the day, so between 8 and 16 hours. And this charging outside of home can increase if we consider more public chargers and public infrastructures instead of residential chargers. And this graph also illustrates how much distances are driven on working days than on weekends. As we can see that from the French travel survey, we have a 25% longer distances driven on weekdays. in this slide, I present the result depending on the residential area. And we also see that the EV diffusion across the population will have quite a notable impact on the energy demand. As we illustrate that in green are the rural areas where more distances are driven, and in blue, the major cities where fewer distances are driven and vehicles getting home later. So with a demand peak at 7 in the evening. Of course, all these results are uncontrolled demand. And in the following steps of my research, I'll try to get some demand with smart charging. And when we look at the connection behaviors, on the graph on the left, we see that in the connection when needed, so which are in red and green, so the green line is on the left is vehicles connect only if they cannot complete their trips on the following day, or if the battery is below 5% state of charge. And we can see that these vehicles connect 1 out of 12 days on average, which implies that a vehicle, a 78 kilowatt-hours vehicle in 2040 can drive without recharging for nearly 2 weeks. And that implies that for a flexibility potential we have to model, we have a relatively low flexibility potential for users that connects only once every 10 days, which is illustrated on the right. And we can see the distribution of the average distribution of times per day per behavior. And in the systematic connection, there is a large window of charge delay, but for the connection only when it is required or only when it is convenient, the window to delay the charge is really narrow. So finally, last results on the what demand data looks like per behavior. And we can see that on the left for battery electric vehicles in red and light green, when the vehicles are connected at the last moment, only when needed to complete the trips, the recharge is spread throughout the night. Whereas in blue, for the systematic connection, where vehicles are connected every day, we have some higher peak demand close to the times when EV drivers get home, and nearly all vehicles are fully recharged at 2 or 3 in the morning. We also added another behavior, which is similar to how people use their thermal vehicle currently, which is plugging the vehicles at the last time, but at fast chargers of 130 kilowatts. It was to study what impacts would be to expect if drivers don't have a recharge infrastructure at home and plug at a public station, at a fast charger and public station. And we see that the demand results are not very far from the daily connection, and there is not highest. The peak is not much higher than the blue curve. And finally, on the right, we see the results for a plug-in electric vehicle. And specifically for those vehicles, we don't see much difference between the connection behaviors, only if the vehicle maximizes the share of electricity in its consumption. So if the user wants to drive most of its distances with electricity, it has to recharge nearly every day. So to conclude my presentation, I would say that I presented a mobility modeling approach for studying the impacts of a large share of electric vehicles. So under this, the most optimistic hypothesis of EV development, we see that personal electric vehicles, and I also included utilitarian electric vehicles, which is 55 terawatt-hours per year in France, which is roughly 12% of total electricity consumption in 2040. We also show that the EV diffusion throughout the population and also the connection behavior of EV users have a significant effect of electricity demand curves and flexibility potential. And in order to go further in the next steps, so I will try to study to integrate these results into a power system adequacy model. So basically using the aggregation approaches described by the previous presentation. And finally, we can also try to study the transport of goods and passengers of heavy mobility in order to complement and take into account the whole transportation sector. So thanks a lot for your attention, and I'm ready for questions if you wish to.
Thank you very much, Remi. Excellent, and right on time as well. Let me see if there are any hands up in the room. Anybody wanting to step in? Okay, well, while they're thinking, then let me ask my question, the opportunity. Oh, yes, a question. That is Patrick. Patrick, you go first then.
Sorry, yeah, thank you. And also thank you, Remi, for this very interesting talk. I learned again a lot, even though the data is very similar than those we have in Germany. I was a bit concerned about your wording concerning the differences in the time on slide number 13, where you said that the earlier the people depart and the later they arrive, the more electricity they consume. At least when I remember right from my studies in statistics, the difference is not significant, isn't it? Maybe you may do a t-test for that.
Yep.
Because I think you're right, it seems to be the case, but especially as I know that you will focus on distribution grids as well, it's very important that you really do the right decisions when you, for example, consider the distribution grid of a rural area, because what you will do, at least what I've learned, is that you will model single vehicles, and therefore I think the right calibration is very important for the modeling and the results, isn't it?
Yep, I totally agree with you. I have not presented the results on the statistical side of the test and stuff because it would have been a bit too long. But what we could see is that from the results of the mobility model, there was a significant difference in the load curve resulting from generating randomly, independently, those two factors, or keeping the correlation as in the data, as in the travel data. And we see that the load curve shifts toward the night if we take into account the correlation.
Okay, thank you. Mm-hmm.
We have some insight on the results rather than on the statistical fields.
Yeah.
But thanks a lot for the very relevant question.
Okay, very good. Remi, my question. You said some of the data that you use is based. Well, I'm not sure about the extent of it, but you mentioned the national trends scenario. That I mean, we know these scenarios are submitted to ENSOs and become part of the 10 by NDP process for identification of infrastructure needs of the sort of integration of European energy sector. And this process is becoming increasingly more difficult with sector coupling and sector energy sector integration and so on. So I think one interesting aspect of what you do is that you bring an interesting sort of argument into the picture and say, because I'm sure the national trend scenario already had a mobility component. Not that I know, but I can imagine it wouldn't be a national trend scenario without one. So when you bring your more detailed probably analysis into it, what can you conclude? Will you be able to see the national trend scenario? You have improved it, or it should have done certain things differently because it has important knock-on effects on infrastructure development in France and in the rest of the Europe going forward?
Yeah, thanks a lot for your question. Yes, so to be honest, I've not finished the study of integrating those results into power systems and the national trend scenario, which is kind of the next step behind EV modeling. But I think the national trend did really a great work, and their focus of study is not electric vehicles. So I understand that they have not taken into account several scenarios and hypotheses on EV development, but rather try to focus on.
My point is the national trends scenario is an important piece of work, and if your results can change that significantly, then you can make a case that these national trend scenarios can be improved significantly because there is a major component in terms of mobility that has been underestimated, the importance of it, and then then people like me can extend the argument across Europe and say, look, these national trend scenarios, they have to be supplemented with more detailed sort of mobility components in these models, because those models are actually very important for development of grid in Europe.
I do agree, but maybe that's a bit of our work as researchers to do some of the sensitivity analysis and add some scenarios. I know that the NSOE won't make 100 scenarios of electric vehicles, heating, or residential demand and everything. They can also focus on a central scenario, and it's part of our work to try to explore the most extreme scenarios. So yes.
Very good. Any questions from the floor? Hands? I'm not sure if I see all the hands. Then I'll ask my last question as well. About DSOs in this picture, you don't directly deal with them as such, right? You are focused on the transmission grid or so. So what kind of assumptions do you make on their behalf so that you can do your analysis? So do you assume that nothing happens in the DSO sector going forward, or?
Yep, that's a really tough subject to study, the interaction between the use of flexibility for TSOs and DSOs. It's really hard to model everything, and in our study we'll strictly focus on TSO and see what is the revenue and electric impacts of electric vehicles at the national scale. Without considering DSO constraints, maybe that's another field of study. But yeah, that's something we keep in mind, that the flexibility of electric vehicles are not only for this topic, but also for other markets and specific subjects like DSOs. Yeah.
Yes, well, I appreciate
that. And just to complement what Remi was saying, and he cannot say because he's working for a TSO, is that cooperation between TSOs and DSOs are said to be easy, but in practice they are far from being any kind of easy. So both of them are working on similar questions, but each of them are developing a different approach. and a different methodology, and then they have to imagine what would be the reaction of the others. But we could say that they should work hand in hand, and from time to time, the French regulator forced them to work hand in hand, but it's never a happy marriage. It's more a forced one with two companies that are separated with different objectives, motivations, etc., etc. So let's say that DSOs do their business, TSOs do their business, and when they are forced to, they exchange the data, but it's not something that they build together to have a common understanding and nor an agreement on how to use the flexibility that would be provided by a fleet of electric cars. It's more like independent work.
Well, now we are going to have a EDSO in terms of association, so maybe things change a little bit going forward in the future.
Hope so.
Yeah. Well, thank you again, Remi. Thanks very much.
Thank you, Remi, for your questions.
We will watch that space. We have an ongoing interest in 10Y NDP. Very good. So let us move on to presentation by Jorge Fernández.
Yes, hello.
A paper being economic and environmental impact of long-term scenarios of low emissions mobility in Spain. Please, Jorge.
Okay, so are you watching the presentation now?
Yes.
Okay, perfect. So I'll start.
Please.
It is possible to reduce the emissions and energy consumption provoked by road transport, but are the targets of transition towards electric mobility realistic? Good afternoon, I'm Jorge Fernández, student at IAEE School of Engineering in Madrid, Spain, and I will present the work Economic and Environmental Impacts of Long-Term Scenarios of Low Emissions Mobility in Spain. A transition towards an electrified transportation is occurring nowadays, and our main objective is to analyze the situation of mobility and transport, to know how urgent this issue is. I will also present you the mathematical model developed and used in this work. Finally, this presentation will end up with the conclusions and possibilities of future work to fully evaluate the electrification in the mobility sector. Transport is responsible for 25% of CO2 total emissions to the atmosphere, from which 75% is caused by road transport. That is the reason why organisms from all around the world have implemented measures and targets to tackle this harmful effect on the environment. Besides, it should be pointed out that the final decision to buy an electric vehicle depends on the consumer. It requires a deep analysis in the long term, and the municipalities have an important word to say. It is necessary to model in detail the fleet of electric vehicles, both the existing and the new one. It should also be considered the use of the vehicles, the age, and the division between urban and non-urban to fully understand the dynamics of the evolution of the fleet. The existing models focus on optimizing costs or welfare. Energy-based models include transport in an aggregated way, while transportation models focus on the run distance and model demand properly. Once the existing models have been analyzed, let's talk about the innovations that the model used in this work includes. First of all, its main goal is to fully understand the dynamics of transition towards an electric mobility. It depends on a detailed characterization of the existing and future vehicle fleet, and it is based in two principles. First, scalability, the possibility to link other models that estimate the electric vehicle demand as inputs. And second, replicability, as this model can be used to study other ways of transport and other countries' mobility. Finally, it is an open source model that can be found in the webpage below. Apart from the database, some parameters can be modified depending on the case scenario that to be studied, like the fleet in 2051 divided into traction technology, or evolution parameters like the year of the beginning of transition and its relevance. Furthermore, the model is an interdisciplinary tool that allows different sectors to take part in the modeling process. It supports sectors related to transport, such as the economical, regulatory, social, or technological fields. Other important aspects is that the optimization process can be replicated to any type of transport. The first part of the model is the tank-to-wheel model, which considers the efficiencies of the fueling of the tank and traction technologies. It is based on hypotheses about the demand. In our case, we have supposed mileage should be constant. Database considers 4 aspects. First, importance of historical information. Second, deduction of trends like mileage, emissions, and energy consumption. It also distinguishes motor technologies and age of cars. And finally, all parameters are dynamic, which means that they change due to the use of the car, to the technical improvements, and to mandatory regulations. The aggregated annual driven distance, both in urban and non-urban areas, is modeled as a function of the age of the vehicle, based on historical information. The older the car, the lower the annual driven distance, as defined by the parameter β-dis. The objective function of the model fits the objective driving distance for every year, both in urban and road travels of the study period, calculating the number of new and retired vehicles of each technology fulfilling the total mileage. The fleet is divided depending on motorization, year of registration, and year of study. The decommission rate is a function of the age of the vehicles. The replacement rate is the result of an optimization problem. This problem matches the constraint of demand of urban and road mileage. Finally, the sales share per technology depends on technology maturity, represented as a sigmoid curve for new technologies. These mathematical expressions are shown as examples. Excessive detail will be avoided in the following slides for clarity. Energy consumption depends on the distance, type of driving, motorization, and age of the vehicles. And emissions are a function of consumed energy. Another remarkable part of the model is that it permits obtaining results classified by various qualities, like the ones we can see in this slide. The well-to-tank section adds to tank-to-wheel results the consumption and emissions in the transforming processes and the historical energy balance. This is especially important in the case of electricity generation. This slide shows the process followed by the model from left to right. It starts with the final fuel consumption and ends up with energy consumption in the extraction and distribution processes. Results are similar to the tank-to-wheel model, energy and emissions. The well-to-tank model combined to the tank-to-wheel model represent the full value chain starting in the extraction process of the primary energy, shipping, processing, and transportation to the gas station, or transmission through energy networks to the charging station. The result of this part include the zone, domestic, or imports, where the resources are obtained, measuring energy dependence, and where emissions are produced. Within the objectives of economic and environmental sustainability, the European Union has proposed a set of objectives for transport that pursue reducing emissions by 55% from 1990 to 2030, and to nearly all passenger cars, vans, buses, as well as new heavy-duty vehicles that will be zero emission by 2050. These objectives have been transferred to national policies in Europe with specific targets for the introduction of zero emission transport. In order to correctly define these objectives, there's a need to develop evaluation tools that allow the impact of each of these policies to be analyzed and taking into account the specific characteristics of this sector. From this slide on, some examples of the results will be presented. It should be pointed out how slowly changes occur. Here we can see the evolution of the fleet of passenger cars in Spain. These results are based on trends associated with the integration of new technologies in the fleet, the steady improvement of conventional fuel-based vehicles with higher efficiencies and lower emissions, and the decarbonization of power systems. Also, difference between well-to-wheel and tank-to-wheel are more noticeable in electric vehicles because of electricity generation losses. Results are obtained not only for type of engine, but also per energy source, also distinguishing between domestic sources of energy and imports. Under the hypothesis of this electromobility scenario by 2050, Spain could reduce by half the imports of energy dedicated to passenger cars. Although it is expected a high penetration of renewable generation by 2050, still combined cycle power plants running on imported gas should be required to cover part of the energy consumed by electric vehicles. Related to the emissions, results show that there is a 70% reduction on CO2 emissions from 2020 to 2050, which is encompassed with the power generation conversion or renewable sources. Moreover, there would be a 90% reduction on NOx emissions in urban areas in the same period. In conclusion, the proposed modeling of the transport sector adequately allows to study the longer-term effects on the economic and environmental changes. In addition, it requires the characterization of the power generation portfolio and accurate technical information of the different fleets and technological trends for transportation. Related to the impact of the electric vehicles, the expected transition towards a more sustainable transportation takes time, and Spanish energy dependency becomes relevant after a decade towards electromobility, which emphasizes the need of national agreements with a long-term vision. Besides, environmental benefits are identified with the reduction of emissions previously presented. For future work, a more accurate analysis should also consider other transport alternatives, and it would be critical to coordinate other models from different fields in order to complete this model presented. This is the end of the presentation. I hope you found it interesting, and thank you very much for your attention. If you have any question, I'll be glad to answer it. Thank you very much.
Thank you very much, Jorge. It was very interesting and very much in line with what I would expect to come from Comillas, and knowing how the colleagues over there, they work comprehensive and detailed. Very nice. Patrick has a question for you. Okay, please, Patrick.
Oh, sure.
Yes, thank you, and sorry for questioning again. Yeah, but I also find it very interesting, George, for this insight into the Spanish perspective. I was wondering a bit about the modeling itself. I appreciated pretty much that it is open access, so probably we can have a look on that. That's very nice. But concerning the method itself, I was wondering myself, how would you classify your model? Is it more agent-based, or is this more system dynamics because what I've seen, I was not so sure about that.
Oh, if you want, I can go back to the slide where
Yes.
the, okay. Let me find it. Okay, for example, this one may be nice for explaining to you. Okay, so I would say our model is like a classic optimization model, which has two main objective functions, which are the mileage, the total mileage of the fleet, and obviously the results, the energy consumption and emissions. And in my opinion, the agent base will come later because we still have work to do. And I thank you for your question, because it's a really nice area to keep on working.
Yeah. Okay, and about the calibration, I think on one slide you said that the older the car is, the less mileage it does.
No, it's a constant mileage.
Mm-hmm.
Yeah. Let me. Okay, it's a. I think it was over here. Yeah. The function, the objective function is a constant mileage, and the old vehicles are less used, and they have a coefficient, and which means that the distance they run is less than the new vehicles. And the aggregate is the constant mileage.
Okay. And where did you get this reduction of mileage from? Is it such an estimation, or did you really calibrate this factor somewhere from the statistics?
It's from the national. I know how to translate. I would say the national association that inspects the fleet in Spain.
Okay.
Yeah.
And there's more or less a constant factor for most of the cars. Okay, that's interesting.
Yeah.
Okay. Yes, probably I can stop with my further questions, or do I still have time? No, there's another question from Remi. I will keep my questions for later.
One more question, and well, I see Remi's hand up. Let me go to him first, and then maybe you can comment back.
Yep.
Please, Remi.
Sorry, so my question was, it's also a question I've been asked before, and I did not have a good answer. So I'm asking you if you have your point of view on this question. It's linked with the representation we had earlier this afternoon on shared mobility and the new usages and evolution of mobility behaviors. How do you think the new technologies and shared mobility can affect the individual vehicle usage in Europe, and to what extent does it has an impact on our results?
Okay, thank you for your question. In this case, the usage of the vehicles and the evolution of the technological the technology is an input for the model, and it has a coefficient, same as we said with the usage, that improves every year the distance that these vehicles can run. I don't know if I answered your question or you have.
Okay, thanks a lot. So it's possible to take into account shared vehicles, and as the speaker said earlier, he said that one shared vehicle can replace 12 individual vehicles also in the fleet. But yeah,
the case we have in Madrid is that lots of companies have settled here, and now there are a lot of options of car sharing and electric scooters and motorcycles. So it is true that these companies of shared mobility are every time getting introduced in the vehicle fleet, and I would say that is a little bit what we have here in Spain. But that point of the study, we haven't done it yet, but I'll tell my colleagues in the team to study it. Thank you.
Thanks a lot.
A quick comment, Anna, if you turn your camera on, then we have all the speakers visible for the last few minutes. I think that would be nice. Yeah, excellent. Jorge, my question, I'm told, I'm not sure how accurate it is, that in Spain, there is currently a sort of overcapacity in the grid. How does that compare then your calculations in relation to compare with some of the other countries? For example, then can we say load shedding and load shifting and so on, it matters less because there is already a sunk cost in the grid and so on, and so there is there is more room for you don't have to worry about so the investment has been done. Its introduction of EVs is can be done with sort of more flexibly also. Am I wrong?
No, you're absolutely right, because as you said, we have overcapacity here in Spain, but in our case, we didn't take it into account. And for the other question you had, the load shifting actually exists, and we have the taxes at the moment. We from the 1st of June, we take them into account. Sorry.
Anybody would like to comment on anything else Jorge said?
Sorry?
I'm inviting any other questions.
Oh, okay. I go in here.
Yeah.
Probably I can have a very short one to George, depending on yes, my question would be focusing on your further research on that, because I may also provide some other literature we have in Germany on open source modeling, which are, I think, quite similar than yours. If this is helpful, I can provide you something. If you continue in this research, of course. Yeah.
Yes,
what is your future plan? Sorry.
Yes, well, our idea is to make the model bigger and bigger. As I said before, the scalability of the model is in the near future is our main goal. So it would be great if we would change our models and open source models. Okay, yeah. I think one example this morning was Carlos from DIW here in Germany was presenting a similar model. Oh, great. And there are, I think, also 2 or 3 others I know from Germany. Yeah. So if you have still the need for further papers, I may provide you ones if you write me an email. Yeah. Oh, sure. Thank you very much. It's hard to give cards to you now in the digital conference. Yeah. Yeah.
We have email for that.
Yeah.
Okay. Any other comments or so? We can spend another 2 minutes or so, but we don't have to if we don't have if we have something else to do.
Yeah, I might have another question if we still have time. So, it's about the electricity generation mix you consider. How much more renewables do you consider in your hypothesis for the emission reductions you showed us, and how do you think the electricity generation mix has an impact on EV impacts, and especially on the smart charging side? Do you think that more smart charging can decrease EV environmental footprint? Yeah, thank you very much again. The number we used was about 70% of impact, and yeah, that number is extracted from the national plans here in Spain, and they have a lot of impact, as you said, in the independence and energy. So that's it. The 70% was the one we used. Thanks a lot. Thank you.
Okay. Well, thank you very much, everyone. It was a pleasure to meet all of you. And I would like to thank our session host as well to make this possible and seamless experience. Thanks again. And I hope you will enjoy the rest of the conference. All of you.
Just a quick reminder for the speakers to upload your presentation on the dashboard. And that's it for me. Technical.
Okay, now you know what to do.
Yeah.
Okay, well, have a good day. Bye, everyone.
Bye-bye. Have a good day.
Bye.
Bye.
Thank
Thank
you.
you very much.